Hey, this is a video for 2.5, Natural Disruptions to Ecosystems. So go ahead and check out the essential vocabulary and set up your guided notes. So when we're talking about disruptions, we have three examples of short-term disruptions, and then we have causes for longer disruptions. So for short-term disruptions or shorter-term disruptions, we have periodic disruptions for one example. And that is an example, for example, we have wet and dry seasons. And this can impact migrations. So these are very predictable. And the migration can be impacted because they are herbivores, for example. They might be following rain patterns. In the oceans, you may have mammals like whales or dolphins that are following warm waters for either feeding or breeding. And birds may follow emerging insects, which is why they will fly down south for the winter and elsewhere during their summer seasons. Now, another disruption is the episodic disruption. And episodic, it's a general time frame, but we cannot predict exactly when. Examples are hurricanes and forest fire seasons. And this can impact the dispersal of seeds or the distribution of seeds. And that's because some trees may germinate sparked by a forest fire. For example, there are some pines that will only open their cones when the temperature is above a certain threshold. Now, random disruptions you cannot predict at all. We know that volcanoes may be building up in pressure. We know, an example is a volcano or an earthquake. We know that volcanoes may build up in pressure. We know that tectonic plates, when they slide past each other, may slip. But we really cannot predict or accurately predict when these will happen. And this can lead to ecological succession, either primary or secondary, and we will talk about this in a video at the end of the unit. Now, longer-term disruptions can be caused by Milankovitch cycles, and Milankovitch cycles are changes to the Earth's. There's two different types. One is the change in the Earth's shift on its axis, and that is referred to as obliquity. The other type of Milankovitch cycle is eccentricity. But for obliquity, it is contributing to natural climate change. Some parts of the Earth are facing closer to the sun or angled closer to the sun, and some are angled far away from the sun. So depending on which area is getting more direct solar energy, that area will heat up faster. Now, eccentricity is how elliptical or how circular the orbit around the sun is. Now, that again can also contribute to climate change. When you're closer to the sun, you may be warmer. When you're farther away from the sun, you could be cooler because of the intensity of the solar radiation. So we have correlated a bunch of data for the last several thousand years, and we have done that by analyzing sediments from the ocean floor and ice core samples from Antarctica. So that has enabled scientists to analyze the temperature, and we don't have thermometers that go back that far, but we do have organisms that were found then that are also found now, and they're known as foraminifera, and they're found in the ocean sediments. So when they take these ocean cores, it's basically a long, giant, imagine a long, toilet paper roll with a bunch of lines, or essentially like a Pringles can that is filled with a bunch of different sediments. And based on these sediments, every year new sediments are added. And if there is a lot of a particular type of foraminifera, they can analyze it and make a prediction or a fair inference to say that they can predict the temperature of that year. Now, likewise, they'll do the same thing with carbon dioxide. So in these ice core samples that are taken from Antarctica, every year that the ice core or that a new layer of ice has been added, they can analyze the bubbles and they can test the amount of carbon dioxide in those bubbles. Now, what they've noticed is that the carbon dioxide concentration of the last, 150 years has increased exponentially, and it is far exceeded the temperature of the last 150 years. So what scientists are assuming is that something is off with the carbon dioxide in the atmosphere, and it's related to human fossil fuel combustion. And this relates to ecosystem resilience and ecosystem resistance. Now, if we're looking at a population of organisms over time, and there's some sort of disturbance, the population will decrease. Now, the population eventually will rebound, and that rebound might not be back to the original population, but it will be better than right after the episode. And the amount of the resistance is, the disturbance is going to affect the energy flow, and that is related to the resistance. So the bigger the disturbance, the less resistant the ecosystem was. And if you notice, the resilience is the amount of time that it's going to be taking to recover. So an ecosystem that has, like we said, has more connections is going to have more resistance to environmental stressors and better resilience. Now, there is a hypothesis, a natural disturbance hypothesis, that there can be, if there's too few frequency or too few disturbances or too many disturbances, the species diversity will be very low. So just the right amount of disturbances keeps the biodiversity high. And if there's too many disturbances, you will kill off too many species. So what I would like you to do is respond to this check for understanding by completing practice problem set 2.5. I hope that this video was informative. I thank you for your attention, and I will see you soon.